In London, 1 litre of petrol costs 108.9 pence. In New York, 1 US gallon of petrol costs $2.83. 1 US gallon is 3.785 litres. £1 is $1.46. In which city is petrol better value for money, London or New York? So with these questions, what we need to do is get everything in the same format. So I'm going to put over here £1 is equal to $1.46. And then I know that if I'm converting from pounds to dollars, I would be timesing by 1.46. And if I'm going from dollars back to pounds, I would be dividing by 1.46. Same with the gallons to litres. I know that 1 gallon is 3.785 litres. So if I'm going from gallons to litres, I am multiplying by 3.785. And if I'm going from litres to gallons, I'm dividing by 3.785. So that's helpful to do just to help focus your work. So in London, 1 litre of petrol costs 108.9 pence. So let's put over here London, and we'll put 1 litre equals 108.9p. And then in New York, we know that 1 US gallon is $2.83. So we need to go so that they are the same unit and the same money. And it doesn't matter which way you go. They've not said you need to do it in pounds or you need to do it in dollars. It doesn't matter. So let's stick with London being as it is. Let's stick with that as it is. And let's change New York. Now we know that 1 gallon is the same as 3.785 litres. So therefore we know that 3.785 litres is the same amount of money, $2.83. And now we've got it in litres. We know that that's the same. So now I want to change the dollars and I want to get that into pounds. So to get it into pounds, I'm going to be looking up here at this rule and I'm going to take 1.46 to go to £1. That is dividing by 1.46. So I'm going to divide this by 1.46 and that tells me what it is in pounds. So that is £1.94. I'm going to write a few more digits though, 938356. Let's just keep it like that for a minute because we're still going to need to go on and do more to that answer. So I know that 1 litre in London is £1.89. There we go. And I know that 3.785 litres in New York is this much. So what we need to do is get 1 litre, in which case we need to divide by 3.785 and also divide this side by 3.785. So I'm going to take that answer on my calculator, divide it by 3.785, and that is 0.512115. But whatever it is, we can see that it's much, much cheaper. So I'm going to say New York is cheaper. And we can see that 1 litre in New York costs that and 1 litre in London costs that. Okay, question number 4. There are only blue pens, green pens and red pens in a box. The ratio of blue to green is 2 to 5 and the ratio of green to red is 4 to 1. So blue to green, 2 to 5 and green to red is 4 to 1. There are less than 100 pens in the box. What is the greatest possible number of red pens in the box? So what we've got here is 2 ratios, but green is 5 in this ratio and green is 4 in this ratio. And it would be helpful for us if they could be the same number. So I'm going to make them both 20. The reason I'm choosing 20 is because 20 is the first number that's in the 5 times table and in the 4 times table. So we can times them both up to make that. I've times this ratio by 4, so this one needs to be 8. I need to also times that by 4, and I've times this ratio by 5, so I also need to times this by 5. And now I know that the pens are in the ratio blue to green to red, 8 to 20 to 5. Now that adds up to 33. So there could be 8 pens, 20 pens and 5 pens in that ratio, which would be 33 pens. Great. But we know that we can make it bigger than that because there can be 100 pens in total maximum. So I'm actually going to times that by 3. Reason being is because that's how big I can go before it goes over 100. 33 times 3 is 99. So let's make this as big as we can. I'm going to times this by 3, which is 24, times the middle one by 3, which is 60, and times the number of red pens by 3, which is 15. And so that is as big as we can make it. That's as big as we can go. We can't add any more pens because we would go over our ratio. We'd go over 100. It says there are less than that. And we want to get the greatest possible number of red pens. So that's going to be this one here. So that is 15. Okay, question number 6. Here is a rectangle. The length of the rectangle is 7 centimetres longer. So it's not 7 centimetres, it's 7 centimetres longer than the width. So let's call the width x, and let's call the length x add 7. Then this one would be x, and this one would be x add 7. Now if x was 2, then this would be 9. If x was 3, then this one would be 10. So we can see that that works to keep it 7 bigger no matter what x is. 4 of the rectangles are used to make this 8-sided shape. The perimeter is 70. So whenever they tell you the answer to something, we want to make an equation, come up with it ourselves using the way that we would work it out. And we've got to work out the area. So I'm going to go ahead and label each of these sides with what we know they are. There we go, x add 7, x add 7. Now there are a couple of sides that are a bit tricky. This one here isn't x or x add 7, but because we know this bit is x from here to here, we know that this bit is just 7, because x add 7 is how wide we know it is altogether. And the same over here, if this bit must be 7 because this bit is x, and we know it's x add 7 altogether. Therefore, the total perimeter of the shape wouldn't involve that one, and it wouldn't involve that one because they're not on the outside, they're on the inside. The total perimeter is going to be all of these added together. So I can see that I've got x, 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 and x. So altogether 1, 2, 3, 4, 5, 6, 7, 8x. Add, and then I've got the, let's do a different colour. 7, 7, 7, 7, 7, 7. So 6 lots of 7, so 8x add 42, and we know that that needs to add up to 70 altogether. There's absolutely nothing wrong with writing it all out, like x add 7, add 7, add x add 7, add x. I've just trying to make it a little bit quicker and more efficient by collecting them all up at the same time. So nothing wrong with that, and then collecting it up. Good, so we're going to solve this equation. What we do to one side, we're going to do to the other. So I'm going to take 42 away from both sides. So 8x is equal to 28. And then we're going to divide both sides by 8, which is 3.5. And this was a calculator paper, so you can chuck that in your calculator if you want to. X equals 3.5. So now I know that x is 3.5, it wants me to work out the area of the shape. Well, the shape is made up of 4 of these rectangles, and each of them is 3.5 wide, and we know that the height, or the length, is 7 longer, so this must be 10.5. And then to get the area of that shape, we're going to do base times height, so 3.5 times 10.5. Let me just quickly pop that in my calculator. 3.5 times 10.5 is 36.75. And then we're going to times that by 4 because there are 4 of them making that shape all together. So 36.75 multiplied by 4 is 147 centimetres squared. And that would be your answer for that one. That was 5 marks, that question. So well done if you got that. Okay, question number 8. When a drawing pin is dropped, it can land point up or point down. Point down or point out. Lucy, Mel and Tom each dropped the drawing pin a number of times. The table shows the number of times the drawing pin landed point down and the number of times the drawing pin landed point up for each person. Rachel is going to drop the drawing pin once. Whose results will give the best estimate for the probability that the drawing pin will land point up, and give a reason for your answer. So the best estimate is from the person who's done it the most times. So more trials is more accurate. The more times you do it, the better idea you've got of what's going on. So who did it the most? Well, Lucy did it 45 times and Tom did it 25 times, but we can see that Mel did it 80 times. So I'm going to say Mel, she did the most trials, or did it the most times. Stuart is going to drop the drawing pin once. Use all of the results in the table to work out an estimate for the probability that the drawing pin will land point up the first time and point down the second time. So, how many times did it land point up altogether? I'm going to do 31, add 53, add 16, and that is 100. So it landed point down 100 times. And then I'm going to do 14, add 27, add 9, because of course combining everybody's data is going to be the most accurate. So we know that the probability of it landing point up, because that's what we want it to happen the first time, is 50 out of, how many times did they do it all together? 150. And then we want to multiply that by the probability of it landing point down for the second time. So point down is 100 out of 150. And we're going to multiply those two things together. So typing that in my calculator, that is going to be 2 over 9. Wonderful. And that's your answer for that one. Okay, question number 10. There are only blue counters, yellow counters and green counters and red counters in a bag. A counter is taken at random from the bag. The table shows the probabilities of getting a blue counter or a yellow counter or a green counter. Work out the probability of getting a red counter. So probability adds up to 1. It is certain that one of these things is going to happen, and therefore that's 100%, which we know in decimals means 1. So if I've got 0.2 and 0.35 and 0.4 so far, that adds up to 0.95. So 0.2 add 0.35 add 0.4 equals 0.95. I'm then going to do 1, take away that 0.95, which is 0.05. And that must be the probability of red, so that it all adds up to 1 altogether. What is the least possible number of counters in the bag? Okay, so we need them to be a whole number. So I can't have 4 counters in the bag, for example, because that would be 1 of each and that would be the same probability for each of them. So which is the smallest probability? Well, that is red. So red is 0.05, which is 5%. So let's say that that is just 1 counter. Let's say that that is 1 counter. Then if 5% is 1 counter, then I know that 40% here is going to be 8 counters, 35% or 0.35 here is going to be 7 counters, and 0.2, 20% is going to be 4 counters. And this is 1, and that would be the smallest number of counters. I can't make it any smaller than that, because then that wouldn't be correct for that probability. So 1 add 8 add 7 add 4 is going to be 20. So 20 counters is the least possible number of counters in the bag to keep those probabilities correct. Okay, question number 12. Alan has 2 spinners, spinner A and spinner B. Each spinner can land on only red or white. The probability that spinner A will land on red is 0.25, and we can see that there. The probability that spinner B will land on red is 0.6. The probability tree shows this information, and we know that each of the branches needs to add up to make 1, so we can see that each of those branches does indeed add to make 1. Alan spins spinner A once, and he spins spinner B once. He does this a number of times. The number of times both spinners land on red is 24. Work out an estimate for the number of times both spinners land on white. So let's start by working out the probabilities. To work out the probabilities, we times along the branches. So the probability of getting red and then red again is 0.25 times 0.6, which is 0.15. The probability of landing on white and white again is 0.75 times 0.4, which is 0.3. And we don't really care about the others here because we're not really interested in that happening. We know that it lands on this 24 times. So 15% is the likelihood of it happening, and that equated to 24 times. So if something is double as likely, like this is 30% rather than 15%, we would expect double the number of times it would land on that. So instead of getting 24, this would be 48. There we go. And that was it, 3 marks. Very nice question. Question 14. Cone A and cone B are mathematically similar. So that means one is just a bigger version of the other. They're in proportion. Let's draw them something like this. Okay, great. The ratio of the volume of cone A to the volume of cone B is 27 to 8. Now remember that when we are enlarging shapes, the lines might be a certain amount bigger. The area is that linear scale factor squared, and that volume is the linear scale factor cubed. So for when we're enlarging shapes, we have how much bigger the lines are, which is the linear scale factor. We have how much bigger the area is, which is the area scale factor. And then we have how much bigger the volume is, which is the volume scale factor. So they're different. In this case, we're told that the ratio of the volumes is 27:8. So that is our volume scale factor. That is how you get between the volumes. If you were told the volume of this one, you'd need to divide by 27 and then times by 8 to get to the smaller one, and vice versa. That is the ratio between their volumes, but it would be different if we were looking at the lengths, and it would be different if we were looking at the areas. So we know to get from the linear scale factor to the area scale factor, we square the numbers, and to get from the linear scale factor to the volume scale factor, we cube the numbers. So that's going to come in handy in a minute. It says the surface area of cone A, let's go, oh no, A is the big one, isn't it? I should have drawn them the other way around. So this one's A and this one's B, because it says the volume to the volume A to B is 27:8. So we know that A is the bigger one. And then it says that the surface area of A, which is the bigger one, is 297 centimetres squared. That's surface area. So in order to get the surface area of cone B, I need to use the area scale factor, which is this one here. So at the minute, I know the volumes are in the ratio 27:8. Now, it's no coincidence that they are cube numbers. We're going to need to cube root those numbers to find out what the linear scale factor is. So the cube root of 27 is 3. And the cube root of 8 is 2. So the linear scale factor is in the ratio 3:2. The area scale factor, therefore, we are going to square to get to. So the area scale factor is in the ratio 9:4. So if the bigger one is 297, we're going to divide that by 9 and then times it by 4 to get to the surface area of the smaller one. So we're going to do 297 divided by 9, which is 33, and then 33 times by 4, which is 132, which we've done. There we go. So we've clearly shown the scale factors for lines, areas, and volumes, and then we've shown our working to get the same answer as them. If we have a show that question, you want to ignore their answer entirely and come up with it on your own terms, in your own way. That was another 3-mark question. Okay, question number 16. The petrol consumption of a car in litres per 100 kilometres is given by this formula. Petrol consumption is 100 times the number of litres of petrol used divided by the number of kilometres travelled. Nathan's car travelled 148 kilometres, correct to 3 significant figures. Okay, so this number has been rounded. So we need to use upper and lower bounds for this question. The car used 11.8 litres of petrol, correct to 3 significant figures. So that number has been rounded as well. We know because it says correct to 3 significant figures. So that tells us it's already been rounded. Nathan says, my car used less than 8 litres of petrol per 100 kilometres. Could Nathan be wrong? You must show how you get your answer. So he is looking to find out how much he used, so the petrol consumption. So let's have a little look. 148 is how far his car travelled. Now that number is going on the bottom of the fraction. So if we're trying to make the answer as big as we can, because he's saying it used less than 8 litres of petrol, we want to make the answer as big as possible to see if he's wrong. Now if we're trying to make it as big as possible, we want to divide by the smallest possible number. Now with 148, if that's been rounded to the nearest 1, which it has because we can see that that is the 3rd significant figure, we're going to go 0.5 above and 0.5 below. If you've rounded to the nearest 1, you half that, and that goes half above and half below. So 148.5 is your upper bound and 147.5 is your lower bound. That's the biggest and the smallest it could have been before it was rounded to 148 to 3 significant figures. So we're going to use the smallest one. We're going to put that on the bottom. So the number of kilometres travelled, let's say it only went 147.5. Now for the numerator of this formula up here, we want the number of litres of petrol used, and we can see that he said that's 11.8. But again, that's been rounded to 3 significant figures. So your first significant figure was in the tens column, your second significant figure was in the ones column, and your third significant figure is in the tenths column. So it's been rounded to the nearest 0.1, which means we're going to half that and put 0.05 above and 0.05 below. So therefore, this could have been 11.85 or it could have been 11.75. And because we're trying to make this as big as we possibly can, I'm going to use that upper bound of 11.85. So it's going to be 100 multiplied by 11.85. Typing that all in my calculator, I'm going to press that fraction button first and put 100 multiplied by 11.85 on the numerator, and I'm going to put 147.5 on the denominator, and that gives me 8.033898. So we can see that actually, using that calculation, his car could have used more than 8 litres of petrol per 100 kilometres. So we're going to say Nathan could be wrong. Always when they ask you a question, you want to answer them, Nathan could be wrong. Now, if you weren't sure which bound to use, just try them. Just try this one, try this one, try this one, and try this one, and just make sure, see if you can get the biggest answer. But if you're trying to get the biggest possible answer, you want to do a big number on the bottom and you want to divide it by as little as possible. If you think about having a pile of sweets and you want to get as many sweets as possible, you want to divide it or share it with not very many people, and that's going to mean you get the most sweets. Okay, here is a speed time graph for a train. Work out an estimate for the distance the train travelled in the first 20 seconds. Use 4 strips of equal width. So what I'm going to do for this is use my straight line tool, and I'm going to make 4 strips underneath the graph. So one there, one there, one there, and one there. And to get the distance, we're actually going to do the area on this graph. You might think about this formula, speed, distance, time. And if we cover up D for distance, the multiplication that we're left with is speed and time, speed multiplied by time. Now in this case, speed is on the y-axis and time is on the x-axis, so it makes sense that we're multiplying them together, getting the area of the graph if we want distance. Now the problem is that we can't do the area of a curve, not at GCSE anyway, so we're going to need to make these into rough triangles and trapeziums to estimate the area. Now, there's a few different ways you can do it. You can use the trapezium rule, or you can just split it up into triangles and rectangles, and I think that's how I'm going to do it today. I'm just going to split it up just to make it a little bit easier. I think it makes it more accessible to everyone if we just work with triangles and rectangles, and everyone knows how to do those, so it just keeps it nice and accessible. The distance covered is the area underneath the graph. So the area of this bit, first section, it's 5 wide, and it is, now let's look carefully at this axis, 4, 3, 2, 1. So 2 squares equals 1 on the y-axis. So I can see that that is going to be 2 high there. So 5 times 2 divided by 2, this has an area of 5, and we're dividing by 2 because it's a triangle. For the next bit, I know it's 5 times 2 for this bit, so this is 10. And for the bit above, I've got 1, 2, 3 on the triangle times 5, which is 15, and then divided by 2 is 7.5. For the rectangle here, this next section, it's 5 wide and 5 tall, so that's 25. And the triangle is 5 tall and 5 wide, but we're going to divide it by 2, so that is 12.5. For the next bit, it's 5 wide and 10 tall, so that is 50. And the triangle at the top is 5, 6, 7, 8 tall and 5 wide. 8 times 5 divided by 2 is 20. There we go. So all together, let's add that up. I've got 5, add 17.5, add 37.5, add 70. They're the 4 different strips in total. I've just done that one, that one, that one, and that one. And just adding that in my calculator, 5 add 17.5, add 37.5, add 70 is equal to 130. So that train, has gone 130 metres in the first 20 seconds, roughly. It's an estimate because we had to draw lines, straight lines, whereas that graph was actually curved. Now, if you look at it, it says, is your answer an underestimate or an overestimate of the actual distance the train travelled? Give a reason for your answer. Now, it's actually quite hard to tell on this one, but if you've got a curve going this way and you've drawn straight lines, you're actually going to be over calculating the area because the curve has gone slightly under, and you can see it just here, the black curve there is slightly underneath the area that we've drawn. So if they've got a curve going like this, your straight lines are going to be an overestimate. If they had a curve going like this, your straight lines would be an underestimate. So in this case, we would say our answer is an overestimate because the lines made a greater area. Oh, greater. Brilliant. That says greater, believe it or not, than the curve. Great. Another 4 marks. Okay, now we've got circle theorem. A, B and C are points on the circumference of a circle centre O. AOB is the diameter of the circle. Prove that angle ACB is 90 degrees. You must not use any circle theorems in your proof. Okay, so the first thing we're going to do here is draw a line going from O to C. And what that gives us then is 2 isosceles triangles. So if I look first at this triangle on the left, I know that this side and this side are equal because they're both the radius of the circle. So we've got an isosceles triangle. So therefore I know that this one is x and this one would be x. We don't know what x is, it could be anything, but it's definitely going to be the same on both, so we can call them both x. And then the same on this side. I know that this side here is equal to this side here. So therefore that makes another isosceles triangle. And then I'm just going to call this one y, and I'm also going to call this one y, because they would be the same. And now we know that all together x add y would equal 180 degrees. We know that that equals 180 degrees because that is all the angles in this triangle, in the whole thing, that we know would add up to 180 degrees. So therefore I know that 2x add 2y is 180, and dividing both sides by 2, x add y would equal 90. Therefore we can see there, therefore angle ACB equals 90 degrees. I think if you've done it once, it makes sense, but you need to see it to be able to then do it in an exam. That was the last one on this paper, so well done if you got that. 34 marks in total. It's just under half a paper. Hopefully you found that helpful. Let me know in the comments if you've got any questions.